So I said that we would do or emphasize some of the points in the calculation, because I won't go into all the details, because for one, we will never get the factors of 2 right doing it live. And for 2, because really some of them are rather straightforward and there is no point in spending our time with that. Also, I want today to finish the XY discussion, because I would like to have 2 lectures to close the various, to have a complete logic for the course, where I will connect to various things we have seen and to various models. So I do want to have the last 2 lectures for other things other than XY. And the main topic of the next lectures will be random walks, which looks like something very different, right? We are studying spin chain models, tables, and I'm telling you random walks, right? Which are random paths of particles, say, in a lattice. But as we will see, standard random walks are very much related to our table. And polymers, which are random walks that cannot cross, are very much related to the kind of ON models like the XY that we have been studying. So in fact, everything will, I hope, close nicely. But today we do want to finish this XY discussion, where we were studying this gas of vortices. And the goal was to do a renormalization step where we want to integrate out UV degrees of freedom, which means that we want to integrate out configurations which happen at very small distances when we have, say, a pair of vortices, a plus and a minus vortex, that are very close by, right? So really think about it like you have a lattice, and things happen at the lattice scale, which is like nanometer. But when you look, you can only see a millimeter. So you don't care about what happens between 1 millimeter and 1 nanometer. You want to start with a nanometer description, integrate out until you say, now my resolution is 1 millimeter. Because I want to study correlation functions. I want to put a spin here and a spin here separated by 10 centimeters. So, okay, my cutoff should be like 1 millimeter, half millimeter, not nanometer, not microscale. So I want to integrate out things that happen at very short distances, because then this gives me access to long distance physics, where I have some cutoff which is much bigger than the fundamental cutoff I start with. Okay? So if I want to understand what survives at large distances, it's equivalent to say I should integrate out what's happening at very small distances, so that I have some effective description that describes things at millimeter scale rather than nanometer scale. That's the idea, the physical picture. Okay, so what did we say? Well, if I want to integrate out, rather than summing over configurations where the vortices are A apart, let's sum where they are A plus delta A apart. So now they are a bit, I increased my cutoff. Well, but that's wrong. This is not equal to that if I replace the integration. I said this is wrong because I'm missing configurations where the vortices were between A and A plus delta A. Right? Because I said now they need to be further apart than A plus delta A. What about the ones like this, where I have one vortex here in the center and one vortex in the orbit of it? I could even have 2 such pairs. Right? This could happen here, and it could also happen here. Rj and Rl could be closed by A plus delta A. So it could happen many times at the same time, and I would be missing those configurations when I approximate the partition function by this. Right? And I would also be missing configurations where I have one center and 2 guys in the orbit, like 2 moons, which are close between A and delta A. So all those configurations we miss when we say that we go from A to A plus delta A. Right? We miss configurations with several planets with moons, and we miss configurations where we have one planet with more than 1 moon, or planets with 1 moon. And here we are only taking into account the configurations where we have 1 planet and 1 moon going around, and nothing else. Not when this happens twice, not when we have 2 moons. And that's the idea of our approximation, that there should not be that many vortices. And so the configurations where 2 are closed, they are already unlikely. 3 being closed and 4 being closed, or 2 being closed separately, that will be negligible, and we are not going to take it into account. When is that true? That's true when we have a small chemical potential, when we pay a big price whenever we insert some vortices. So we should self-consistently check at the end if indeed the number of vortices is small. If we finish our computation and we say at large distances I have a huge amount of vortices, well, then this was wrong. Right? So this will be true as long as the density of vortices is small. So let's hope that this is true. We'll check it at the end. So if it's true, then this is a reasonable approximation. I can replace the cutoff by A plus delta A, and I include these configurations where two guys are close to each other at the center and at an orbit. Who do I choose to be the center and the orbit? I can choose any of them. So there is n times n plus 1 and n minus 1, and I choose one to be the center, one to be the orbit. So there is a factor of n squared. And then I have to integrate over the remaining positions, over the center and over the orbit. And I want to integrate out the center and the orbit. I want to integrate out these bound vortices. Now notice here that this prefactor is of the same form as that one on the partition function, on the leading term, after I take out a factor of k squared and redefine what I call n. Right? So if I take this factor here, is this, and then I could call n equal n prime plus 1, and then the action is of the same form as above, but with a factor of k squared here. Right? And n prime would be the number of remaining vortices. Okay, good. Now, what is the action here? Well, the action is exactly the same as before. The other vortices still interact normally. There is always this pairwise interaction between the other ones that were far away. But then we have this term, which is the interaction between the planet and the moon with all other vortices. Right? And this term, the planet and the moon interacting with the vortices, we could expand out. And then we write this expansion here that I wrote up to here, plus this term that we studied in the lecture. Okay? So this is just expanding when the separation to the center is much bigger than the separation between the orbit and the center. Okay? Then when we expand, we see we expand down the exponential, and there are various terms. So for example, this term and this term that we studied in the lecture, they come with j squared. That means we expand the exponential twice. And all other terms come with a single power of j, which means we expand the exponential once. Okay, fine, both, we need both. But we truncate at terms that are quadratic in our orbit. Because because our orbit is small compared to the distance between Ri and Rc. And we don't truncate at linear order because the linear order by symmetry just vanishes when I integrate over the orbit. So the quadratic term is crucial. The quadratic in orbit we can easily integrate. We can very easily do the integral over the orbit using integrals like this. Right? And then so that's the first step. We integrate over the orbit, our orbit. We integrate over our orbit. That's the first step. And the second step, we integrate over the center. Okay. So after I integrate over our orbit, for example, in this expression here, I integrate over the orbit, and I still got something that depended on the center. For example, in this term, and this was the toughest term, and that's what was the one I chose to describe. After I integrate over the orbit, I have an interaction between I and center, and between center and j. And then, as I said, that you integrate out the position of the center, and this will generate some effective interaction between I and j, which is just whatever is the result of this integration. And it just turns out that, as we saw last time, that this is of the same form as before. So it is just changing giving me some effective coupling between particles I and j. In fact, you see that if you do it a little bit more carefully, let's try to understand what this integral should give. So what are the dangerous points of this integral? What are the interesting points in this integration over the center? We have when the center approaches Ri, that gives me a logarithmic term. When the center approaches Rj, that also gives me the same logarithmic term. Okay? Because it explodes as 1 over the distance when I'm approaching there. So when I'm approaching this point and this point, it gives me a logarithmic term of Ri minus Rj. But I also have an interesting point, which is when the center goes to infinity. When the center goes to infinity, this is 1 over r to the 4. Here, I get r center square. So it's 1 over r center square. So when I go to radial coordinates, it becomes 1 over r center. So it also decreases logarithmically. So it also gives me a log L term. That's just from the terms when the center is very far away. And the claim is that most terms in this expansion cancel. So let me tell you how. So this one is just 0 by symmetry. Okay. This one, I integrate over the center. I go to radial coordinates. And you see that if I go to radial coordinates, what will this term give me? Just a logarithmic divergence. So this term here gives me a log L. Nicely, this log L cancels with the log L that we got here. If we did the computation carefully. So that's what will happen to this term. It will just regularize the other one. Actually, sorry, maybe I did it too fast. It was too fast, sorry. Not true. Not true. It is this term here. This term here. This term here, after I integrate over the orbits, I generate some effective interaction that once I integrate over the center gives me a log L. So it's this term here that cancels with that term here. This term with a -1 also generates a log L, and that one cancels with this term here. So these two terms will both generate a log L, but they cancel. Of course, the ones I said could not cancel between themselves because one has j squared, the other has j, so they could never cancel each other. But these ones, they come with the same power of j and they cancel each other. And so this term, half of it cancels with this term, half of it cancels with the log L of that term. And in the end, the only term that survives is some effective interaction between particles I and j. So what will I give? What will I get? I will get that our z, I put both terms together, so I write it as sum from n equals 0 up to infinity, k to the 2n over n factorial square, integral product dri, ri minus rj bigger than a plus delta a. Now I change the cutoff, and we get exponential of minus 2 pi beta j minus, and here I'm going to write 16, but actually I did not have time to check factors of 2. But if it's, you will see that it doesn't matter. It's just overall factor of 2 later. 16 pi cube beta square, or let's write like this. Okay. J square beta square k square a cube delta a times log of Ri minus Rj over A. There is also one term. This is from everything, and there is the 1 here. Right? What will the 1 give? The 1 will give the area of the shell of the orbit, which is 2 pi, which is just 2 pi times delta A, 2 pi A delta A, times wherever this can happen. Right? So it gives me the area of the surface times 2 pi A delta A. So I can say that that term just renormalizes my Z. So there is some renormalization here, but that's just normalization that comes from the 1 in the expansion. That's just the fact that there was some volume of where we could put the vortex that just got renormalized into some renormalization of Z. It will not affect any averages we compute.
What about the Ni and J?
Oh, I probably forgot, yeah. That's super important. Ni and J, right? Sum over I not equal to J.
Are there also supposed to be more Ni and J's in this line over here?
Here, there was an Ni and J missing, of course, yeah. Ni and J. Here, no, here just Ni.
Why is that?
Because this is Ni interacting with a plus and Ni interacting with a minus. So it's Ni times 1 and Ni times minus 1, and that's why it became ratio of inside the log.
So we're assuming that these two...
Yeah, we are assuming that these two vertices, one is a plus, one is a minus, and therefore they can disappear. If they would be plus, they could not disappear. They would have non-zero vorticity. I could not just integrate them up.
What's the justification for saying that that won't happen?
That's you could try to see what's the effect of if they would not be 1 plus and 1 minus, they would not be a small effect. They would double. So the small effect, it's when 1 is a plus, 1 is a minus. Then it's 1 plus something small. When both are big, it's a very big effect. And what it happens is that the vortices don't want to get close to each other when they have the same sign because they repel. Right? So vortices of the same sign, they attract, so there is some chance that they stay together. Vortices of opposite sign, they repel, so they are not going to be together. But more physically, we never integrate out things with charge. It would be like saying that I have some particle with charge and I integrate it out. No, I mean, if I have an electron, I make a circle and I see, I ignore what happens around the electron, but okay, whatever it is, there is some charge minus 1 inside. I cannot just say, electron disappeared, right? So, but here the point is that vortices repel and opposite charges attract. So the ones that would have opposite charges, they would be close. The other ones would not. Now, let's see importantly what happened here. So here we say that this quantity here is therefore some 2 pi beta j prime, where this prime stands some effective. This is some effective coupling at the new cutoff. Now, this is step 1 of renormalization. So this is step 1 of Rg was integrate out degrees of freedom that we don't know of, like when they are very short distance. There is a step 2 now. And the step 2 is to rescale back so we can compare. Let me explain this step. This is just convenient. This is a convenient but an important step. So we started with some configurations, right, of vortices. And we said that there is a scale, there is some radius where they cannot approach much. Right? Then we went to some, then we did step 1 of RG. And after step 1, we get the same kind of vortices. But where now the cutoff is bigger. Now I have a bigger cutoff. Right? And I want to next step, what we do, we rescale such that the new cutoff is what I call units. Right? The original step, if you remember, this A was just an artifact. This was just 1 or 2, whatever. Now it changed. So now, instead of 1, it's like, let me put in quotation mark, like 1.1. We increased it a little bit. But then if I want to compare again, what I want to do is call this my new cutoff. So call it 1 again. And what I want to ask is, in this new picture, where I rescale, do I get in this new picture something like this? Or do I get in this new picture something like this with more vortices? Right? So it's after, if I don't rescale, I'm not comparing the same thing. I'm saying with respect to my cutoff, am I getting, when I'm integrating out, are the number of vortices increasing or decreasing? So I integrate out, and I have a huge gas, and then I rescale such that the cutoff is the same. Now this picture, I can put on top of the other one. I put these guys in red, the original in blue, and I'm seeing, did the density increase or decrease? Okay? So now, in this picture, we would say that there would be less vortices, which means at large distances, which means vortices are not important. And if we get this kind of picture, we would say that as we zoom out, we see more and more vortices. And therefore, vortices will dominate. Yes?
How would you ever get more vortices from rescaling?
So after you integrate out, you want to know if but let me show you mathematically how that will happen in the exercise, but in what we are going to do next. But to be able to answer that, you would have to know what is happening everywhere. Right? You have to keep in mind that because you are rescaling, right? Because you are scaling down again, there will be more vortices than in this picture, because as I zoom out, as I zoom in, more vortices that were outside the plot range now come in. But on the other hand, some vortices disappeared, because there were vortices that in this picture, they were like this. Right? So some vortices disappeared, integrating out, but the rescaling brought some vortices in because of rescaling. So at the end, in the new picture, do you get more or less? And it's a competition of both. Right? So here, we could have this picture. Let's do more rigorous. Let's say we have this vortex as well. Right? And now, in the new picture, after I integrate, this one disappeared. Actually, if this guy is a pair, and this is a plus, and this is a minus, in this picture, this guy disappears. after I renormalized. And then I rescaled, and after I rescale, okay, let me put this guy still here. And now I zoom out, and the new guy appeared that was not in this plot, but as I zoom out, this guy appeared. Right? But here, maybe, let me put one more. Okay. So here, maybe still there are 4, and there were 5. There were many. But here, there could be many more. So there could still be less, and here still much more. Let me give you another example of the importance of these 2 steps. And to do it, I want to anticipate something that we are going to do in the next time, related exactly to these random walks. Okay? So let's just do in pictures RG for random walks in pictures. So I start with a random walk, which means that I have some particle that is moving randomly. And this is a huge random walk, so there is much more. So it describes some very complicated figure, which was totally random. Now, this is a random walk. It means that this, for me, is like my cutoff, is what I can see. I can see these small steps. That's the resolution I have. But I could say, I want to go to a larger cutoff where, for each steps here, so let me see. Can you see if I write with this color here, red? Can you distinguish the red from the white? Yeah? So now I took 2 steps and I joined them into 1. So this means that now my cutoff is twice as big. So I don't resolve the individual steps. I join each 2 steps into 1 step. And now I get a picture like this. This goes here, then here, then here, then here. You see the pattern that I'm getting. I'm joining just 2 by 2. Right? Now, if you look at the new path, of course it's different. The steps are much bigger. But you are not going to, but what you should, yeah?
Can you backtrack?
Sorry?
Can you backtrack?
No. No. The question was, can you go back? If I understood correctly. No, that's the idea of RG. RG is you integrate out things, so you don't see anymore. You zoom out.
Can the random walker backtrack?
Yeah, here, for example, it went a few times. Yes, it could backtrack. Yeah.
But in the same step, like to the right and then to the left.
In this term, you see that here I'm not drawing lines going vertically and horizontally only. I'm drawing lines in all directions. So I'm not considering a random walk on a lattice. I'm considering a random walk with some probability distribution of going into any step at any point. So then backtracking exactly, it's never going to happen. But we are going to describe it in more detail. So now what happens is that in step 1, I got some random walk where I have bigger steps. And then what I do in step 2, I rescale to be able to compare both, such that the steps of the new walk would be of the same size 1 as before. And now I can compare the random walk with bigger cutoff with the initial random walk with smaller cutoff. I can see what happens when I'm integrating things out and looking at larger distances. Right? And for example, what we will see is that if you have this picture for the random walk, let's call this figure final, and you started with the white line here, which was figure initial. For the random walk, figure final is equal to figure initial in the sense that you cannot look at 2 and distinguish both. If I show you both figures, you don't know which one was before RG and which one was after RG. right? I just show you two pictures and they look exactly the same. So the figure final being equal, and this equal is in the sense that you cannot tell which one is short distance and which one was integrated out. They are indistinguishable. This is equal to the figure initial. That's something we are going to see. It's not obvious, but I'm telling you. From this picture, it looks reasonable, but it's not obvious. And this is what defines scale invariance or self-similarity. Which means that all distances would be relevant, that you will not be able to zoom in and zoom out and tell at which point you are. The analog case we could expect to find in our model. There could be a critical temperature, for example, where you zoom in and zoom out and the density of vortices would remain the same and you would not be able to tell at which scale you are. And that would be a critical theory. It is one where there is no privileged length scale. And you zoom in and you zoom out and all length scales look the same. Okay? So if this happens, that would mean that all length scales matter. Okay? But this would be two examples of RG. Integrate out, rescale so you can compare. Then integrate out a little bit more, rescale again so you can compare. You do it several steps, and that's what is an RG group. Okay? So together, this step 1 and step 2 are what are called the RG flow. Okay. So that's just another example in pictures to anticipate what we are going to see in the next lectures. But now, let's then do this step. So rescaling, what does it mean, this rescaling step? It means that you change R to R prime, or you change A to A prime, which is like an active or passive transformation. So either you say that I'm recalling what I call cutoff. I can say A plus delta A for me is 1 now, and I am basically rescaling A, where I say I rescale R such that I rescale R by how much I rescaled A. And it's up to you. You choose how you want to rescale, but don't do both, otherwise you are doing nothing, right? So either it's equivalent because R is measured in units of A. So either you change A or you change R. Okay? So it really doesn't matter. So it's equivalent, of course. So in practice, what happens? How do we do this rescaling? Well, I would go here and say that this A, the cutoff that appears here, this A, is not the same as the cutoff that appears here, which is A plus delta A. Right? So what I can do is I put here A plus delta A, but then I need to put A plus delta A over A. Right? So now this term here is something I can compare. I have distances measured in units of the new cutoff. The particles are separated by the new cutoff. That's perfect. Right? In that first term. So I just did exactly what I said I should do. I redefined the new cutoff to be 1. And I have this extra term here, which gives me log of this term. So this term will contribute to how? Sum over Ni and J. And the expansion of this, when delta A is small, would give me delta A over A. And then there is this prefactor, which is minus 16 pi cubed J square beta square chemical potential square. And this sum is over j not equal to I. But the sum over all j is 0 because we have neutrality. So this sum is nothing but minus the sum over I of ni square, which is just minus the number of minus twice 2n, because ni square is 1. So it just counts how many there are. And therefore, this new term, you see, is just renormalizing now my chemical potential K there. See? So in rescaling like this, as I expect, I am now redefining my chemical potential. So I can absorb that orange term there in putting a prime in K and redefining K prime. Yeah? So this term here is basically telling me that the action becomes of the original form, where K prime is, let me write, K plus 2 pi beta j delta A over A. That sounds very wrong.
Is that like J prime?
Yeah, there are many factors missing here, right? So let's see. So there are pi's missing.
No, it's correct to first order delta A. Right?
Sorry?
It's correct to first order delta A.
To first order in delta A. It's just from that term there. You are right. So to first order in delta A, 2 pi j delta A over A from that log there. So what I shouldn't have done is put this, because this is second order, right? I should not have written that. I should have written here. You are right that this comes already with A cubed. So the leading term comes from the 2 pi beta j. It's this term that matters. Right, so 2 pi beta j, that sum gives delta A over A. So this is just effectively changing K prime by this amount. So the claim is that zooming out, integrating out a little bit a cutoff, I say that the model, I went from a model with coupling 2 pi beta j to a model with this coupling and this chemical potential. Okay. So this is what I would get here. If here I started with some model which has parameters beta j and k, I did this step, and now in this picture here I get beta j prime and k prime after I integrate things out and rescale so I can compare.
Can you make a comment on the beta j prime in terms of dimensions? Because it doesn't seem that both terms have the same dimension in terms of dimensional analysis. Is there some scale that...
Beta j is dimensionless.
But A is not, right?
A...
Kappa is dimensionless, but then you have there a volume.
Kappa, yeah, kappa is not dimensionless. Kappa is not. Kappa.
But then the expression for kappa prime would be also off now.
Okay, I think I will answer your question right now. Because these equations, now I'm going to rewrite them a little bit. That's exactly related to something that Andres is saying, which is that you see that the variable that is changing is beta j. Here I get beta j square. Here I get beta j, so all good so far. But here I get k, and here I get k square and a cube. So I want to write equations where I don't have all these powers of a floating around and I'm dealing with dimensionless quantities, and that's what we are going to do now. So let me write how the equations, how you would like to write these equations. What's the best way? And it's like this. Let's write a summary. So we have 2 pi beta j prime is equal to 2 pi beta j, the original cutoff. Let's try to write it. And then we have 1 minus, and you see that there is there some 2 pi beta j that I would like to factor out. If I want to call this variable, I will want to call this something, clearly, because this combination appears a lot. So there is already a 2, there is a 2, so I would have 2 times 2, 4, I need 16. So I would need a 4 here. So that 4 would be here 4 pi square k times a square delta a over a. So hopefully I did not forget any factor. 4 times 4, 16, okay. Sorry?
Only pi.
Only pi, not pi square. Probably all right. Okay. Okay. Let's pray. Okay. And now I see that what we would like to do is to define these variables. Now this combination is what appears here. So delta A over A is dimensionless. So this is what we will call delta L, where A is just e to the L. It's just I do a rescaling. So L would translate a little bit. So we went from L to L plus delta L. Okay, so we rescaled a bit L. This is dimensionless, right? So A would be something like this if you want, times some A0, where this A0 for us was just 1. It was the original lattice spacing. But then we did a small rescaling. So this is dimensionless. So then I want to call this quantity here. I would like to define this quantity. Let me define also with a 4 pi. I want to define this quantity to be y. But what I have is the transformation of k prime. So what I want to write next is I want to write k times a square, and I want to say by how much this quantity changes, because this quantity is the dimensionless quantity that appears there. Right? So I want to define by how much this changes, right? And I can put a 4 pi just for convenience. And by how much does this change? This changes by, I'm going to write it, there is 4 pi k a square. So I just multiplied by a square, and I copy from what I wrote there. Sorry, 1 second, because this is important. Yeah, I don't, okay. Here it's a minus sign. Here it's a minus. Be careful here. Okay, well, I'm not, okay. We'll have to do carefully, but the correct result is a minus here. And that's going to be important now. So this would be 1 minus, and then what appears here would be 2 pi beta j minus 2 times delta A over A plus. So let me explain what we did here. To close the equations, we said that I want to put k close to a square, and that's exactly to make it dimensionless. But now that I put k together with a square, I have to take into account that a transforms to a plus delta a when I transform it. And therefore, it introduces this extra minus 2 in the equation. That's just from the transformation of a. That's just from this a here, by putting the a explicit. Because now the equation's closed, right? Now the equation's closed. You see that the fact that each k carries units 1 over a square is exactly what we need, such that for each integration, I have, for each particle, I have a 2-dimensional integration. So together with a k, I get a dimensionless quantity. So k has natural units of inverse of the area of a particle. Yes?
I have two questions. Firstly, over here, why can you bring down that 2 pi beta j? Should that not be in the exponent?
But delta A is small. So delta, right, no, but you are right. There is some mistake here, sorry. You are right that it's in the exponent, but it's small. So it's the same as 1 plus downstairs. But then it multiplies k. You are right, right? K multiplies everything. So you are right that I forgot here a parenthesis. 1 minus this. Okay? It was in the exponent, but it was a small infinitesimal perturbation, so I can always bring it down. There is no difference between writing k times exponential of this or just k times 1 minus this, because I'm working to expand. This is an infinitesimal transformation.
Hold on, so this, sorry.
Now, can you repeat how you got to that k prime? Because so k itself depends on a, right? It's exponential log of 1 over a, right? Shouldn't that also contribute to?
No, no. K is whatever k is. It's a number. It's my chemical potential, right? You can't. I think you are doing active and passive at the same time. You are doing too many transformations. So k is k. Right? So transforming a in k like you are proposing is not equivalent to changing r. It's not equivalent to doing a dilatation.
But
you can't transform things too much. So k is just, I started my chemical potential that had some value when I start in the UV. I can't start transforming things here. So what I do is I rescale r. Okay. So let me just explain the mathematics here. So here, it was just, I forgot a bracket. 1 minus this. So this k to the n is multiplied by exponential of this quantity to the n. So the new k, let's write here the new k, k prime, would be k times e to the minus 2 pi beta j delta a over a, right? So this you would be happy, right?
Wait, is there not a log there though? Like it's log.
What log? You mean this log here?
Yeah.
No, but this, when I did this, it's the fact that log of a plus delta a over a is delta a over a. Right? I separate this into two terms. The first term, after I rescale r, this is just the same as setting this cutoff to a again. Right? So we multiplied and divided to separate, because now I get this term. The first term is of the same form as the original form, where distances are measured in units of the cutoff. The second term I have to massage, but the second term, log of this, is just delta a over a. The sum over I and j can be done explicitly and gives just counts number of vortices, and therefore this is just modifying the coupling like this. But this is to linear order, so I can expand down the exponential and I get that.
Okay. I'm sorry, I have another question then. What, when, I don't know what you mean by this k a squared prime. Like, this, there's the beta j prime already has the ka squared, so are you transforming again, or is it like...
So I'm saying that under a dilatation, right? Under a dilatation, a square, right? A square changes under a dilatation to a plus delta a square, which is a square plus 2a delta a, which is a square plus 2a square delta a over a. So if I put an explicit a square, under dilatations, I should add a plus 2 delta a over a times a square to my transformation. The reason why I'm doing this, I'm asking, under dilatations, under changing a to a times e to the L, how do the parameters change? But I want my equations to close. So I could remove the a square. So I could, this is also true. If I remove this, I remove here, and I remove the 2. But then the equations would not close, because here I have a quantity y, here I have a quantity that I will call x, here I have x, and here I have a new one, which is k, not y. So if I want the equations to close, if I want to have a finite system of equations that close, that I can iterate several times, I need to transform k appropriately, and k has dimensions of 1 over area, so this is the appropriate quantity I should write.
What do you mean by close? What do you mean the equations to close?
Okay, sorry, good. It's good that you asked this question. So let me write what do I mean by that. So now that we see that we have here y, it's tempting to define, let me define this quantity to be x. And then by equations closing, I mean that then these equations are equivalent to the following set of equations, which tell me that dx dl equal to minus x plus 2y squared, and dy dl is equal to minus x times y. So it's in this precise sense that in terms of these defined equations, in terms of these renormalized couplings, I call this y, right? This is y and this is x. In terms of these quantities, which are dimensionless parameters, how they change when I rescale a little bit L, how I zoom out, is now encoded into 2 differential equations. They are closed in the sense that they have 2 differential equations for 2 variables. I can now solve them.
The rescaling, you are putting this as e to the L because that's the scaling that comes from the partition function.
I'm just, in writing this, I'm just saying, I'm just introducing L here in saying that dilatations now are shifts in L. Shifting L, increasing L or decreasing L amounts to now doing dilatation. So having a differential equation in L tells me what happens as I'm making dilatations. This tells me under a small dilatation, how much do the parameters change. It tells me that this one, for example, if these 2 guys are positive, this guy decreases when I do a small dilatation. And if these 2 guys are positive, this tells me that this guy also decreases when I do a small dilatation.
But if you choose that way of dilatation, is that part of your renormalization scheme? Or does it comes naturally from the partition function?
You see that all I've been doing here in the second step was make sure that all quantities are dimensionless. So L is dimensionless because it's by how much I dilate, and these combinations are dimensionless. So it is just, it has to be. The final equations, if they are nice, they must be for dimensionless quantities. But in the intermediate steps, I was not super careful because, for example, here we are adding up quantities that have different number of integrations. So of course, this k needs to be dimensionful. Otherwise, I cannot add up things with different number of vortices, right? I cannot add 1 plus a double integral plus triple integral. If the double integral has dimension of L squared, triple integral has dimension of L cubed, I cannot just add them up. I need something to absorb the dimensions. So K, each K absorbs the dimensions of one integration. So it has units of 1 over A squared. See? So in other words, I could have put here, from this point, at this point, I could have defined the K tilde and define each integration to have a factor of A squared. And then everything would be dimensionless. And then you would never see K. You would always see K tilde, and I would immediately land on this final equation that I wrote here. And you would never see K in the intermediate steps, right? Because from the beginning, I would define dimensionless chemical potential, dimensionless beta J, everything would be dimensionless, and then I would never need to do this. But I think this is more instructive because normally we are not super careful from the beginning. And what we should do is we look at the equations, and I want to close the equation. So this I want to write as derivative with respect to scaling factor. Here I have a variable, here I have a variable. This variable I want to call something. And if this something doesn't appear in the other equation, I better redefine the other equation such that it does, such that I get an equation that closes.
Sorry, so this 4 pi k squared prime should be 4 pi of ka squared squared, because that's what you have in the first line.
Sorry, can you repeat? So here I have 4 pi ka squared. I chose to write this on the left-hand side because it's what appears in the first equation.
What appears here is ka squared all squared. So, like, am I missing something?
Ah, no, you are probably... yeah, this is suspicious. So you are right. So, yeah, so let me count. Yeah, you are right. This is wrong for sure. So this I want to, according to that equation, this is y squared. I'm defining this to be y squared. So then here I should put not 4 pi, but square root of 4 pi. So 2 square root of 2, and here 2 square root of pi. Yeah. And then this would be y. That's why you're right. I'm not confident about powers of pi, and I don't think the square root of pi is right. I think probably I forgot some further pi's. I could count them. So I have 2 pi to start with. Then I get pi squared because I brought it down twice, J. And I got an extra pi from the integration over radial coordinates. So this pi cube looks good. Pi cube, but I only put a pi there. So then I would have to put that square root. That might be okay, actually. Yeah, that's probably okay. Yeah.
So are we supposed to have x plus 2 squared there? Because we have two pi beta j factors in the first equation.
Yes. Yes. Good. Oh my God, so many mistakes. So a prime, a, let's see one more time, y, x, yeah. I think finally this is correct.
Oh, hold on, I don't.
Sorry?
I can't see that I don't agree that there's a square somewhere, but like you have what you have here is x prime is x plus.
So this, right? This is what happens when I change a plus delta a. So this term minus this term is the derivative with respect to delta a. Right? So to convert it into a differential equation, I bring this term to the left, I bring this term to the left.
Okay.
Right? Because this is an infinitesimal change. So I write this guy as derivative times delta a. I divide everything by delta a, I bring it down. So it's just the derivative form of that. So, right? In other words, I could put delta x here and multiply by delta L there. Delta y here and delta L there.
Could you explain the minus sign in the expression for k prime? The one you are currently standing in front of.
Ah, this minus sign? Oh no. Okay. This minus sign is super important, and I hope I didn't do a mistake in putting it. Let's see. So delta A over A gives this, gives delta A. There was a minus, right? So there is an overall minus there. So there is a minus here. Then there is a minus here. So in total there is a plus. And in total there is a plus. So yeah, that's because, yeah, as I said, some paper, yeah. Yeah. It is just changing the sign of J. It is just that probably, but to be fully consistent, I'm also not 100% positive about this sign. So what I know is that these equations are good if you follow things carefully, with the starting point being perhaps an overall minus in the exponent, but the final equations are correct. Okay? So there could be an odd or an even number of mistakes in signs. So I can redefine beta j to be minus beta j. When I do beta j equal minus beta j, I flip a few signs. But right. So right now it looks like this sign is suspicious here overall. And I think probably actually I don't have it in the beginning, right?
I think it's
Okay, good. So that's the explanation. So there is no sign here. Then there is no minus here, and then everything is okay. Whew. By the way, today is the toughest lecture for sure. I think this is beautiful, but it's a bit. All these things are a little bit subtle. So do ask lots of questions, like Evin is asking. I think it's good. This is indeed a bit. This is subtle. Okay, so we got these differential equations that tell me how do I go. So these differential equations are what govern what happens when we start with this picture with some A, and we did a rescaling, and we went to some A0 e to the L, and so we started some A0, we did some rescaling, and this is how the parameters changed from the picture of the left to the picture of the right. So after I integrate short degrees of freedom, I get a model that is of the same form as the original model, but where the parameters x and y changed according to this differential equation. So that tells me how I got some effective beta j and some effective chemical potential after I integrate out degrees of freedom. And now you see what I was telling you before, that we start with some chemical potential. Let's assume it was small. There was not that many gas. And we integrate out, and it better be that the chemical potential decreased. Or at least it didn't increase a lot. Because if it starts decreasing, we are okay, because then those configurations that we ignored it was justified to ignore them. But if somehow, as we are zooming out and then rescaling, the y's would become very large, it would be a problem. So what happens here? Well, it depends. We will have to analyze it, but it's not guaranteed that we are in business. So does y decrease or increase when we integrate things out? Depends on the sign of x. If x is positive, it's okay, it decreases. But if x is negative, it increases. So we will see that when x is positive, the chemical potential is effectively decreasing. So effectively, we are going to less and less vortices, and vortices are not important at large distance. But if x is negative, we get more and more vortices, and vortices are important, and we lose control over the approximation we are doing, and we go into what we call the strongly coupled regime, where we cannot trust what we did. Okay? So let's analyze this now. So now it's the important part. But to summarize, the claim is you have a model, and that model, under a normalization, which means under integrating out short degrees of freedom, changes to a new model which has the same form as the original one, but with couplings that changed according to this differential equation, where L is by how much you rescale. Okay? Is it clear? Yeah? So let me draw what happens to this differential equation. So let me draw. So if this is y and this is x, let me draw the flow induced by this differential equation, and I'll draw it and then I'll explain it. So you see that if x and y are positive, what happens when x and y are positive and big, these derivatives are negative. So when x and y are positive and are sorry, 1 second. Yeah, when x and y are positive, these derivatives are negative. When x is negative, this derivative here is positive. So and finally, okay, we will see this in a second. I'll explain this. So here there is a special point, which is the point x equal y equals 0, because under this point, at this point, x doesn't change. At this point, dx dl equal to dy dl equal to 0. That's exactly this point that we drew here with a random walk, where we have scale invariance. Things are invariant under doing dilatations. So this is a critical point. If you are at that point and you rescale things, you get the same thing. Okay. But then, if instead I start here, okay, so this is the critical point, but if you start here, x moves, we will explain how it moves like this. And if you start here, you move like this. Okay, these are what happens if you start with some x0, y0 and then evolve according to this differential equation. So this is not hard to see, because if we zoom in close to this critical point, okay, close to this critical point, x star equal y star equals 0, the equations become the following. I can write the first equation becomes something like dx squared dl, I multiply by x, is minus y squared times 2x. I'm just massaging the equation. So I say that x is close to 0. I multiply by 2x the equation, and the x is close to 0. I'm close to critical point, so this is just 4. And then this equation I can write like this. And the second equation I can write as dy squared dl equal to minus 2xy squared. Okay. Because close to the critical point, let's write here before doing these tricks, we get just dx dl equal to minus 4y squared, and dy dl is equal to minus xy. We ignore the term. We are expanding close to x equal y equals 0. And then this implies these equations, if I did no mistake. I hope I did not. right? I just multiply by 2x and I recognize the derivative. I multiply by 2y and I recognize. Okay. Okay. One second. Yeah, there should be some 8, yeah. So, sorry, give me 1 second. Yes. Okay. Okay. Yeah. I'm not sure about this 8. I am, okay, I am sure. So what this means is that DDL, no, but I really don't like this, sorry. I want to redefine variables so that this equation is a bit nicer. When x equal to 0, this is 4, right? So you see when x equal to 0, this is 4. This is 2, 2 square is 4, and I want that 4 to disappear. So I want to put a 1/4 here. Please stand with me. So putting a 1/4 here means doing what? Means rescaling y. I rescale y by 2. What does it do to the second equation? Nothing. So the second equation is still okay. So all I need to do is go to y and redefine it by a factor of 2. So this quantity, I want this to be, I want this y to be that, I want that y with the, is it times 4 or over 4 here? Please help me.
Times 4.
Times 4, okay. Times 4, it's your responsibility. So now you see how hard this is. Okay, so you put a 4 there, you remove a 2 over there, and then if that is 4, there is no 2 here. Right? Okay, and now with this extra factor, the equation doesn't have a 4 here, and then this is a 2. And then it means that DDL of x squared minus y squared equal to 0. So x squared minus y squared is equal to some constants. And these are the trajectories I drew there. And in particular, x squared minus y squared equals 0 are the dashed lines I drew there. So those are the lines x equal y that separate these two types of trajectories. Now, we see that something very different happens if, depending on where I start. Remember, where I start means my microscopic physics. I start somewhere with some chemical potential and some temperature in the UV, where I have the full model. And then I integrate out degrees of freedom to go to large distances. And now it depends where I am. I could be here, and I flow here, or I could be here, and I flow there. So these 2 points are very different. If I start from here or start from here, my fate when I zoom out is totally different. Right? So what is happening? So let's analyze both cases. So clearly, we have scenario A and scenario B. Right? And depending on where we start, so remember that this x is 2 pi beta j minus 2. So you see that x being very large means beta being very large. So starting at B would mean starting at some beta bigger than some critical temperature. And starting at A would be starting at some temperature smaller than some critical temperature. Right? So what we see here is that if we start at some beta bigger than some critical temperature, remember what this is? This is low or high temperature? Low temperature. What happens here? We start integrating out degrees of freedom, and what happens to the chemical potential? 0. So I start above some critical temperature, I zoom out, and what happens? We go here, where we have no vortices. Right? So what happens in this scenario? So if I start in B, so if I start here and then I follow my RG, I go to some point x0. In fact, that constant I could call this constant here. When y equal to 0, I could call this constant x0 squared. So when I go there, I go to some point x0. Which x0? Right? This x0 depends on where I start. If I start here, I go to another x0 prime. And I can compute, given the point that I start here, which x0 I go. Right? You just compute. And then what is this x0? This x0 is 2 pi beta 0 j minus 2. Right? So this x0 is defining that at this point here, I have y equal to 0, which means no vortices. And I have a temperature beta 0, which is an effective temperature as I'm zooming out. So what do I get here? I get just 1 over, for correlation functions, I get just the low temperature expansion we predicted with a coefficient 1 over 4 pi beta 0 j, which was the prediction for what we got when we had no vortices. We get the Gaussian model. With what temperature? The temperature I start here? No. I have to renormalize, zoom out, and I get some effective temperature here, and it's with this temperature that I should put there. Right? So, but then this beta 0 could be a complicated function. So this x0, this beta 0, is some non-trivial dependence on the starting point. Right? This is your model. Someone else starts with another chemical potential in the UV. So you have some different UV parameters. And you flow, you go to different x0s. So you could be studying the same vortex model, for example, same temperature, but you use 2 different chemical potentials. Right? But same temperature, but just with slightly different chemical potentials. You zoom out, you go to 2 different x0s. So that just means that this position is very non-universal. You change the microscopic parameters, you change where you go. So this is definitely non-universal. Very much depends on the starting point. Right? And there doesn't matter. What would be universal? What would be universal is if I start right here. Because starting right here, I know where I'm going to flow. I'm going to flow exactly here. Right? And what is this temperature here? This is when x equal to 0, which means that I am at this temperature of Kosterlitz-Toulouse that we computed once, which was the 0 of this, just 1 over pi. Okay. J beta Kosterlitz-Toulouse at this point. So if I start with a temperature here that puts me on this line, I flow to this theory, and in this theory, I get 1 over x, and now I put here beta to be 1 over pi to the power 1/4. And now this is universal. In the sense that if I am in the point where I'm transitioning from the point between having vortices and not having vortices, because this is the last point where I still don't have vortices. If I'm here, now I have vortices. So I can tell an experimentalist, measure for various chemical potentials. At some point, you start having vortices. Right before that, the exponent will be 1/4. That's universal. But I cannot tell him, and before that, it will be another power. That power, I don't know. That's very non-universal. It depends on the details of the model. It depends, for example, is it a solid-on-solid model that we described or the XY model? The two will have slightly different chemical potentials, and the two will lead to different physics here. But in both models, when they will transition, you go to this point is 1 over pi, and therefore this point is universal, and it is just 1/4.
So does this mean like if somebody on one scale measures a temperature and then somebody else is on a small person with a small thermometer would measure a different temperature?
Yes, it would mean that. Yes. So at large distances, if you are at the largest possible distances, you flow the Rg until the end. But if you are at shorter distances, indeed, you are right that if you are at very short distances, for example, if you are here, right, you are flowing here, and if you are here, you are flowing here, and if you are here, you are flowing here. All these three curves, at this point, they look very similar. It is only later that they start deviating. So what's the physics here? Why are the curves so similar? Here, we are in a regime where the scattering length is much bigger than the separation we are studying. So here we have huge scattering lengths. So because we have, not scattering length, huge correlation lengths. Yeah, you replaced, right? You did the replacement. You have huge correlation lengths. So here, if the distances are small, I did not see yet that things decay exponential, for example, with the vortices, because I'm inside the correlation length. So I see effectively a critical point. And as I'm zooming out, the vortices time to be important. So the same trajectories, as I'm zooming out, now this trajectory, and this trajectory are super different. Now I clearly can distinguish them. So before I'm at short distances, I have some big correlation length, I can't tell yet. But then as I zoom out, the trees start to look very different. Yes?
So when x changes, do we interpret that as a change in J or temperature or both?
That's not physical because only dimensionless quantities are. So the physical thing is beta times J. Right? So you to measure temperatures in units of inverse coupling, or you measure couplings in units of temperature. The only thing that makes sense is beta times J. Beta never appears alone, or J. You always get beta J. So that's the only physical thing. In fact, most people don't call beta J. They just remove J or beta. So if you look at the paper, it will have just e to the minus J or e to the minus beta. They never put both. I'm putting both because you are instructed to put e to the minus beta times the Hamiltonian. The Hamiltonian had some J, but it's a bit, it's not very logical to keep both. So what we see here is if I start on this side, so you see, notice that I start with some y, right? And suppose that I start with my chemical potential here. Let's say this is 0.2, for example. Then y is small, the chemical potential is small, right? And I evolve it, and it just became smaller. So it was good. It was a good approximation. We ignored some vortices, and as we zoom out, it's less and less and less. But not here. Here, eventually, it kicks out. So here, I would not know what happens. I just know that vortices are appearing, many vortices. My approximation is not good for sure. Why it's not good for sure? Because we were working to leading order in K. We were saying K is small, so I keep K squared, so I keep 2 vortices. But I don't keep K4, I don't keep K cubed. But now we are seeing k is becoming very large, so those nonlinear terms were important. So I couldn't have dropped it to start with. So here, as we live, so here, the RG is not valid anymore. But our interpretation is that if I am on this side, I am at high temperature, so beta smaller than beta critical. And here, because the vortices appear, I would get exponential decay. Of correlators. Okay? Let's try to estimate the correlation length with which it will decay. So it will decay exponentially. So let's try to ask, what is psi? But before, we could ask, what is the critical temperature? So this is the first question I want, and this is the second question I want to understand. And here, we want to ask, what is psi close to the critical temperature? Okay? And here is, first question is, what is the critical temperature? Okay, now, this critical temperature is not universal. Because as I said, it depends where we are on this plane. It's very much depends how you are. But we can compute it or estimate it for our model. So in our model, right, for us, it depends on the various models, but for us, what will at L equals to 0, which is where we start, no dilatation at all. What do we have as a starting point for our equations? Beta j at L equal to 0, no dilatation. Be careful, this L is not a length. It's by how much you dilate is e to the L. So this means no dilatation. This is beta j that I measure in the lab. And what was the chemical potential at L equal to 0? I remind you that we computed this. It was exponential of pi beta j that we put in the lab times log of R0 over A that we are starting the RG flow, so it's 1. And this R0 we computed. It was this Euler gammas and so on. And this whole quantity is approximately minus 1.6. This was computing this R0 that you remember. We computed this. This R0 was 1 over 2 square root of 2 e to the Euler gamma. So this log is minus 1.6. But what's important is that you start with some beta j for your microscopic model in the lab. And these two equations, they describe a curve in the plane yx. Right? As I change beta j, I change this, which is related to x up to some simple shift. And I change this, which is y. So changing beta j means changing a curve in xy. So I can draw this curve. And if you draw this curve, you find, if you draw this curve, x, y as function of x parametrically, where beta j changes there, we get some curve like this. So here, I'm changing, this is changing our microscopic parameters, beta j that I put in the lab. Okay. This is the line given by these two equations here. Okay. And now you see that this line, I can now ask, when does this line intersect this point? When this line intersects this point, this defines a beta critical, a critical transition. So what I have to solve is I find this curve, y that is a function of x, right? I impose that this curve is equal to x, and in solving this equation, I compute the intersection of the dashed line with this line, and I extract what is beta critical. Okay? And that would be the critical temperature for our model. Someone else has a different model. That just means that someone else is in some different curve. This curve would be other lab that uses fluctuating surfaces rather than XY model, for example. Or someone uses Sine-Gordon, which is yet a slightly different curve. So different microscopic models will give different curves here, and therefore they will predict different critical temperature. For us, in the approximation we did, this is a good estimate of the critical temperature. Yeah. So this would be different microscopics. Our microscopics is this, is the statement that when I start, I know what my K is this, and that gives me a starting point. So you see that you can now just intersect this curve, and this will tell me what beta critical is, and you will see that beta critical is not 1 over pi. Remember, this was the naive guess. But there is, if you solve this equation, you get something, I don't know, 0.18, or I forgot exactly. And this would be a small correction from this RG analysis. Okay? And if you do the Monte Carlo problem that Lauren prepared for you, you will find a value that is much closer to the RG corrected value than it is to the naive guess. Now, let me emphasize something. This is the critical temperature in the sense that if I have my microscopic model, the one that I will simulate with Monte Carlo, that's the beta parameter where I will go from power law behavior to exponential behavior. Right? You see? Now, when I'm moving that temperature, I am not getting power laws where the beta that appears here is that temperature. The beta that appears here is I start with some beta in this curve, I see where I am, and that's the effective temperature that I see in my power laws. And in particular, at the critical temperature, I don't put here the critical temperature, I put here the Kosterlitz-Toulouse temperature that is 1 over pi, and I get 1/4. Okay? So one thing is determining the critical temperature. When do I intersect the critical line that separates the two behaviors? And one thing is, and what is the endpoint of the flow? So I first start on a very non-trivial curve. And then for each point on that curve, I have to solve these differential equations that I only did to leading order, close to the further, and I shoot somewhere there. And then, after I am at the fixed point, I read off the exponents that are very non-universal, of course. Right? So they depend non-trivially on where I am on the curve. And then I have to solve the differential equations that see. I only solved it with an approximation close to the fixed point, just to draw these curves. But if you solve it in a computer, you can draw better than these arcs here. You can see that maybe it's a little bit off. You just solve this differential equation. So, and that will be the prediction for what the power law behavior is. Okay? So let me just now final thing. So yeah, I'm going to go 5 minutes over time at least because I'm just trying to close the XY model. I'm not going to, next time I'm not going to make a summary of XY and so on. So next time it's really, I will not summarize anything. It will be a really fresh lecture on the random walks and then making connections with what we have seen. So I really want to finish XY now. So let me, so you have to, so let's continue a little bit more. I think 5 minutes should be enough. Let's, for example, so we said a lot about the low temperature phase. It's pretty awesome that we can say so much and so non-trivially. I mean, and this is beautifully explained in the papers of Kosterlitz and Toulouse. And it was then verified experimentally, and that's why they got the Nobel Prize. I mean, you can imagine that you predict here, you start with this curve, go here, predict this exponent, and then you measure, and it works. It's super awesome. So indeed, this was the Nobel Prize of 2016. understanding this transition, which they did using renormalization in the way that I explained you. Now, let's ask, how could I estimate what's my xi close to T equal to the critical temperature? So now, I want to ask that I'm here, I'm close to the critical temperature, so there was this line, and here I am some distance apart, so I am some epsilon or some alpha times T minus the critical temperature. So I separate a little bit from the critical temperature. So linearly to first approximation, I am some distance away, which is proportional to the deviation from the critical temperature. And then I want to ask, what's the correlation length? So I want to ask here, what's the correlation length? So what do we know? We know it's very large. Why is it very large? Because there, I cannot distinguish that model from a critical model. The trajectories look exactly the same in the beginning. And that is the statement that there, in the beginning, my correlation length is huge. So I don't see yet, I did not consider distances bigger than the correlation length. Okay? Good. So now, the idea is the following, is that here, so as I said, here, the model looks critical. At this point, I cannot tell the difference between this and this. They are very similar, which means that psi is much bigger than A. It's very large. The critical length is very large. But here, we zoom out a lot. Right? And here, the point is very different. So here, psi, here is not critical at all. And psi would be of the order of the cutoff. So I would estimate psi at this point to be E by how much I rescale L. So I start with cutoff A, and I say that when the rescaling is roughly as big as the critical length, right? So here, when I reach at this point, for sure I'm not critical, because I rescaled as much. So I had some huge correlation length, like 10 centimeters. Right? 10 centimeters is huge, right? This is condensed matter. So we have 10 centimeters. And if I rescale from 1 nanometer to 10 centimeters, at this point, the curves must be very different, because I start seeing the correlation length that I had to start with. So that's how much, this is how much I should rescale starting from here to start seeing the correlation length that I could not see before. Because I make a dilatation until I reach, until A is now, the cutoff is increased by so much to be the correlation length. You agree? So that gives me, that tells me, that's an estimate of the correlation length to see how it scales, right? So we say that psi, which is just some E to the L, which is exponential of the integral of the L, is just how much I make a dilatation. And then I use the fact that I know my flow. I can write that this is exponential of the integral over dx over dx dl. And I can say that I start with some x, and I go to some other x here. And I, instead of integrating in L, because I know this RG flow, I can integrate in x from this point to this point. But dx dl is basically y square, right? Dx dl is y square. And y square is a times t minus tc plus x squared. Or maybe alpha, the way I'm using. Okay? You agree? And now you see that you can rescale x by square root of t minus tc, And then, if these x endpoints are of order 1, just rescaling x, this gives me exponential of some number divided by square root of t minus tc. And the number, I don't know for sure. That depends on the details.
By the time you've gotten all the way over there, isn't the estimation of alpha t minus tc no longer valid, or hasn't it become not?
No. Be careful. So here, let's put A. So here, I'm saying that I determined the critical temperature. Now I'm slightly away from the critical temperature. So T is not defined here. T is defined here on my model. This is, I determined the critical temperature there, and now I change T to be a little bit above critical temperature. So I'm starting here. At this point, there is some scattering length, which is huge, but I don't know what it is. I want to know, what is this scattering length at this point? It's huge. I'm close to the critical temperature, so my correlation lengths are huge. And I don't know what it is. So what do I know? I know that if I rescale my cutoff many times until I reach that correlation length, at that point, the theory no longer looks critical because I reached the correlation length. So I know this correlation length, this one, that is the one I want to find. I could say it's when I did so many dilatations that my x is roughly here, somewhere here, where the curves no longer look the same. Right? When the curves no longer look the same, here the theory is not critical for sure, right? This trajectory here doesn't look like this trajectory here. Now, where is it? Is it here, 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 here? Doesn't matter much because it's some point x of order 1. So there is some point x where clearly you can say, oh, I'm no longer in the critical trajectory for sure, right? So at that value, you know that you are not at the critical trajectory. So you say that e to the L, you want it to be equal to this, because then you are not at the critical. On the other hand, L, how much do you need to rescale? Well, you just need to integrate x from here to some point here. But you know this curve, and this curve is given by this curve is given by y square equal x square plus t minus tc, right? So you can compute the length of that curve there by integrating like so. And this integral gives me exponential of square root of t minus tc, where you just see this by rescaling x to be square root of t minus tc times y. Oh, y is a bad idea, x prime. And then this becomes a number of order 1 times square root of t minus tc downstairs. And we conclude that this goes to infinity as t goes to tc faster than any power law. And that makes this transition rather special. Typically, we get power law behavior for the critical exponent, how it diverges with temperature. And we see that it diverges faster than any power law, which means that experimentally, it's very hard to see this correlation length, because if you are close to the critical temperature, you will get like 10 to the 8 lattice spacings. And of course, you will not see it. You see, it's really, really huge. And you will need to go to super huge lattices to see. So it's very hard, say, to effectively measure this correlation length, precisely because close to the critical temperature, it blows up in this funny way. Okay?
Well, but it seems like that's highly dependent of chosen the rescaling to be of the form e to the L. Because we could have put it, like to put something adimensional, we could have put just something of length over something of length.
So delta A over A, I could define this to be e to the L square, right? And L equals 0 would be no rescaling. L equal 1, 2, 3, 4 will be more and more rescaling. Mm-hmm. That would be just a change of variable in this differential equation. L is nothing special except a parameter that parameterizes this curve. It will not change anything. It will just, right? Because if you call e to the L square, then you tell me when L is 2, I'm here. But I don't care about L equals 2. In your language, I would say, well, 2 means a shift by e to the 4, means you did a dilatation by e to the 4. So once we talk in terms of physical things, which is by how much did you dilate? You tell me, I dilated by 4, me too, so we can compare. Now, I use variable L, use variable L square. Okay, that's not physics. That's what variable you use to coordinatize dilatations. Provided we use dimensionless quantities, and provided we can tell each other by how much did I do a dilatation, it's good. You will get differential equations that look different, but you will reach the same conclusion, of course. This is just a particularly simple one, that the shift, that dilatations, homogeneous dilatation, if I dilate by the same amount each time, I just translate by the same amount each time. So it's a very homogeneous coordinate. But you can use any coordinate to parameterize these curves. It will just change this differential equation, the variables in the differential equation.
How about when we're below the critical temperature? That behavior becomes you get an imaginary.
Below the critical temperature, the correlation length diverges because we get power loss. Below the critical temperature, we know the behavior is power law, so the correlation length is infinite.
But if we look at that expression, is that a power law?
This derivation was not true. This derivation did not hold if I am on
the other side.
On the other side. In the other side, I flow to no vortices. So I flow to no vortices means that I have power law behavior in the other side. So what's the correlation length? The correlation length is when do I start seeing exponential decay at some length. There's no such thing on the other side. On the other side, I go to power law. So on the other side, the correlation length is strictly infinite. So it's strictly infinite on one side, and it blows up faster than any power on the other side as I approach the critical temperature. And on the other side, it's infinite always. And that's the statement that we have a line of critical theories and not one critical theory. So that this model is special in many ways. It's special by this algebraic blow up. Things blow up faster than any power. And it's special because there is a continuum of theories with power law behavior, not just one. So typically what happens is that there is a point which is a critical point, and to the left and to the right I have exponential decay, and at the critical point I get scale invariant. And here we get power law behavior to the left of a point, not at the point. So this theory is in that sense a little bit special. Okay? So the final thing we could do, but I'm not going to do because it's really I'm already way over time, is we could ask, what are the correlation functions of two spins, spin, if I am close to the critical temperature here, which means that vortices are almost important. I should still see some effect of vortices. Right? And the way to compute it, one way to compute it is to repeat the analysis of the partition function for the correlation function. You start with A, and then you go to A plus delta A plus 2 delta A, etc. And you write a differential equation directly for the correlation function that tells you how it changes when you are changing L. And because we already know how the couplings change with changing L, we can integrate out this differential equation. And the behavior that you get is 1 over x to the 1/4 times log of x to the power 1 over 8. And this log correction is an effect of the vortices that you would get if you were to do this integration carefully. And that's an example how we see that the behavior very close to the transition, it has these logarithmic corrections that you interpret as some remnant of the vortices, the fact that there are almost no vortices. So at the end there are no vortices, but along the flow there are vortices. And you can say that this effect is like the result of integrating out all these vortices. It ended up giving some logarithmic correction to the power law at the end. Okay? And that's a more precise estimate of the behavior very close to the critical temperature when T is critical temperature minus some small quantity. Then this would be the behavior you expect. So that's it about XY. So please go through the arguments carefully at home because I'm not going to summarize them. And at the end of the next lecture, come and ask me if you have questions. So I don't want to summarize because what I'm going to do next is really very different. But I do want you to ask me questions because this is a subtle thing. So ask me, or even better, ask Lauren. She's much more of a specialist of XY. I'm really at the border of my knowledge. So any epsilon step, I will start bullshitting. So it's hopefully you ask me questions in the direction I still know. But that's tricky. Okay, so let's see you again on Thursday.